So now we want to describe a technique for computing degrees, and this technique can be applied for most maps that arise in practice. Yeah, so that is, how do we compute degrees of maps? So again, we have a map from Sn to Sn, and we take n greater than 0. So I will draw S2 so as to make this point clear. So you have S2 and then you have another S2. So map F is taking one S2 to another S2. So these are maps such that you take a point Y in Sn. Yeah, you take a point Y in S2 and it has finitely many points in its pre-image. Yeah, so we draw some finitely many points in its pre-image in S2 again. Say x1, x2. So say a total number of m points. Yeah, so the pre-image of Y consists only of finitely many points, and then we draw neighborhoods around these points. Yeah, so these are the disjoint neighborhoods. So all these neighborhoods of these finitely many points are disjoint. Obviously, since there's a Hausdorff space, you can shrink the neighborhood as much as you want to get disjoint neighborhoods. So let us just denote the neighborhood of xi by ui. Yeah, so let me write this down. So pre-image of f inverse y consists of finitely many points and their disjoint neighborhoods are denoted by ui. Okay, so we have the following thing. Yeah, f of ui minus xi, this gets mapped to v minus y. Yeah, where v is the neighborhood of y. So let us draw v. So this v is the neighborhood of y. So this will induce a commutative diagram which we will draw on the next slide, but let us write this down. So this induces the following. So map F induces the following relative pair homology groups. Yeah, so F induces the following map, that from Hn to Hn. Also you can have, so I would denote this map by 1, but you can also say this map is Hn is from Sn comma Sn minus F inverse y to Hn Sn comma Sn minus y. Yeah, instead of ui you can write Sn there, and instead of v you can write Sn, and instead of xi you can write F inverse y. So now I want to recall excision. Yeah, excision, so space X is completely covered by A and B, that is interior of A and B. Then we have the following isomorphism of the homology groups. So we are recalling this fact. So say X is the sphere Sn, A is Sn minus a point A. Yeah, B is just say ui, a neighborhood of point A. So A intersection B will be ui minus A, and therefore we will have so I'm going to write Hn x comma A first. This is x comma A, isomorphic to Hn B comma A intersection B. B is Ui, so just to make it sure that there's no confusion, the arrow mark, yeah, and this I'm going to rewrite on the right side. Yeah, that is pretty much it. So let us denote it by 2, which we are going to use again. So now I want to talk about this thing. Hn Sn is isomorphic to Hn Sn comma a point. Yeah, this is clear from the long exact sequence of the pair Sn comma a point. Yeah, as you can see here, I'm just writing the long exact sequence associated with the pair. So point will give you 0, and therefore you have an isomorphism. Now this is equivalent to Hn Sn comma a disk. So you take a point out of the sphere, what you get is a disk, and this disk is isomorphic to a point. Yeah, you get the dn disk. Take a point out of the sphere, you get d2. Take a point out of the n sphere, you get a disk. Now this is an important point which I think I should have mentioned recap before. So you have a map x to y space x to space y taken by a map f, and A is going into x. So I want to tell you the page number on Hatcher where you can find this. You can find this on page 118. Yeah, so you have A which is part going into x, and then A maps to FA which is included in B, which is again included in y. So good time to stop here and see Hatcher page 118. So how do you get this map? Yeah, so this map is important because this is precisely what we used for number 1. Yeah, so for a recap, just see that this is precisely what we use for number 1, where space x is ui and space y is v. So now we're going to write it like this. You have space x, which is ui, and space y is sn. So notice the following inclusion map. And this will induce the, so I'm not writing f here. I'm just saying that the inclusion map here is producing this homomorphism of the homology groups. Yeah, this happens precisely because ui is just a neighborhood of x. So it does not intersect with other neighborhoods of other points in f inverse of y. So ui is just a neighborhood of xi, and it does not intersect with other points. That is why you can say ui minus xi is included in Sn minus f inverse y, because ui is pretty small. So if it would intersect with other neighborhoods, then we cannot say ui minus xi belongs to that. So consider this other map which I have started drawing in the left side. So take 2 points out of Sn on the left side and take a single point out of Sn on the right side. So we will have the following map. Yeah, again induced by the inclusion maps. So we are just labeling these maps because we are going to use this again. So just notice the label 1, 2, 3, 4 and 5. Yeah, so that is pretty much it.